Okay, we have this mysterious number e, which we've said is the limiting value of 1 plus 1 over n raised to the nth power. Comes directly out of what happens if you look at compound interest and consider compounding more and more and more times as more and more approaches an infinite number of times. And in the limit you get the number e, which is approximately equal to 2.7. Okay, so what's a graph of e to the x look like? Well, fairly easy to do an approximate graph. Of course, we could always plug numbers in and so forth, but let's just do this by looking at the graph of 2 to the x and the graph of 3 to the x. Since e is about 2.7, it's somewhere between 2 and 3, but somewhat closer to 3. Well, okay, let's go ahead and graph 2 to the x and 3 to the x. The tables are very easily made. If we understand how we calculate the values of 2 to the x, we can easily calculate the values of 3 to the x, and these are the values that we get. Now, I did find that people apparently just kind of memorized these values over here and still don't understand that like 3 to the negative 2 should be 1 over 3 squared, and 3 to the negative 1 should be 1 over 3 to the first power, and also 3 to the 0 is 1, not 0. So we really need to understand those things. It's 2 months into the course here. It's something we're supposed to understand the first day of class. Okay, anyhow, so we do a graph, okay, and we do the points of the 2 to the x graph. It looks like this. We graph the 3 to the x graph. It looks like this, and then we say, okay, well, and I guess the e to the x graph is going to be in between these two, and probably somewhat closer to the 3 to the x graph. Now we could always make a table for e to the x, but that's not the basis on which I drew the graph. Okay. Now the one thing we do know, of course, is it's got to go through the point 0, 1. All simple powers have to go through 0, 1, positive powers. And the 2 to the x graph goes through the point 1, 2, 3 to the x graph through the point 1, 3. The e to the x graph, it goes through the point 1, e, and since e is about 2.7, that point would be 7/10 of the way between this point here and this point here. And that's about the way it came out. Okay. We've got a better approximation to e here, but that's irrelevant to a graph drawn at this scale. Now, this is not the table that we used to make this graph, but it's totally compatible. And having made this table, we compared with the graph. When x was 2, here's our graph point we projected over. This point should have been about 7.3 if I did my arithmetic correctly. And I know 2.7 squared is 7.29 because powers of 9. But it looks like we came out a little less than 7 here. So that just means that, okay, I did a freehand graph and I came out a little bit low here. Didn't get it exactly right up here. It should have gone up just a little steeper. That's not a serious problem. We see how the graph of e to the x is located between the graph of 2 to the x and the graph of 3 to the x. Okay. Now, I did the y equals e to the x graph so I could compare it with the graph of y equals 10 to the x, and so that I could do the inverse functions of these two. Okay, so I take the e to the x graph with these approximate values, and I do the inverse function. I simply switch the columns, and the numbers, and now I have a graph of natural log of x versus x because that's what the natural log is. It's the inverse of the exponential function. Now we've done the inverse of the 2 to the x function. We've constructed that inverse, so this is really no different. We've constructed the inverse of the x squared function, although as we saw, we have to restrict the domain. Otherwise, we don't have a function. Okay. similarly, we could do the y equals 10 to the x. It would be very convenient to try to graph this because the numbers go as little as 0.01 and as big as 100, meaning this number is 10,000 times as big as this number, and you're going to have trouble getting two numbers on the same page, getting the points representing the two numbers on the same graph when one of them is 10,000 times as big as the other. We could do it with 2 to the x or even 3 to the x, although it gets a little inconvenient with 3 to the x. With 2 to the x, 4 is only 16 times as big as 1/4. We can actually kind of locate that. Here, 9 is 81 times as big as 1/9. That gets pretty hard to locate accurately in the graph, but this is much, much worse than that. This one wouldn't be too bad if we knew the exact numbers. Of course, our calculator will tell us a good approximation. Okay, now the point is, here's our e to the x, here's our 10 to the x, and we should understand where those numbers came from and how we inverted the graph. I found the inverse function by reversing the columns of the graph. And here now we have a graph of the natural log function, and this is the graph of the log function, the log log function. Okay, so natural log of x is the base e log. Natural log of x equals log of x over log of e. And I should have said it equals log base e of x. Similarly, the inverse of the 10 to the x function is the y equals log x function. So log x is the base 10 log. And actually there's no point in writing what I was going to write, so I'm not going to write it. Okay, log x is the base 10 log, and that's evaluated using the log key. Okay, well, that's what your log functions are. This is a graph of your e to the x function. You can invert these two graphs and you get the graphs of the log base 2, log base 3, and natural log functions. I'll probably just do a real short video and kind of toss those graphs in here. This note just says, do certain problems on your homework sheet.